In this episode, we're going to take the next step after deciding to stop hard-coding secrets, which is figuring out where secrets should live and how they should be protected while they exist. A secret is valuable because it unlocks something, and that means protecting secrets is not only about keeping them hidden, but also about controlling who can retrieve them, when they can be used, and how you can prove what happened if something goes wrong. Beginners sometimes imagine secrets as single values tucked away in a file, but in cloud environments, secrets are part of a system of trust that includes storage, delivery, monitoring, and rotation. If secrets are stored casually, the rest of your security program inherits that weakness. Safe storage is therefore not a nice-to-have improvement, but a foundational requirement for keeping cloud access intentional. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Managed secret services are built to solve the storage and control problem in a consistent way, and the key idea is that you want secrets to live in a dedicated system designed for sensitive values. When secrets live in random locations like shared drives, configuration repositories, or long-lived environment variables, you lose control and visibility. A managed service typically offers a secure vault-like place to store secret values, combined with mechanisms to control retrieval and to record access. It is not magic, and it does not replace good design, but it creates a standard pattern that is safer than ad hoc handling. It also allows teams to build applications that fetch secrets from one trusted place instead of scattering credentials across artifacts. When storage becomes centralized and controlled, it becomes easier to enforce policies and to audit behavior. Encryption is a major part of safe secret storage, but it is important to understand what encryption does and what it does not do. Encryption protects a secret's confidentiality when it is stored or transmitted, meaning if someone steals the raw stored data, they cannot read it without the decryption key. When you hear the term Key Management Service, KMS, for the first time, think of it as a system that protects encryption keys and controls how they are used to encrypt and decrypt data. Encryption at rest means secrets are encrypted while stored, and encryption in transit means secrets are protected while moving across networks. However, encryption alone does not prevent unauthorized access if an attacker can call the system that decrypts the secret on their behalf. That is why encryption must be paired with strong access control, because the ability to request decryption is itself a powerful permission. Access controls determine who can retrieve secrets and under what conditions, and this is where identity and access management, IAM, best practices become essential again. A beginner misunderstanding is assuming that if a secret is in a secure vault, anyone inside the organization can safely access it. In reality, the vault should enforce least privilege, meaning only the specific identities that require a given secret can retrieve it. Access should be tied to roles or service identities that reflect real workloads, not to broad groups that are convenient but overly inclusive. If a single developer account can retrieve production secrets without a clear need, the system is vulnerable to phishing and credential compromise. Restrictive access control ensures secrets are not just stored safely, but also distributed safely. Another important access control concept is separating the ability to read a secret from the ability to manage secrets. Reading is high risk because it exposes the raw value, while managing includes actions like creating, updating, rotating, or disabling secrets. These are different responsibilities and should not be combined casually. For example, an application workload might need read access to one secret, but it should not have permission to create new secrets or modify other secrets. Similarly, a person responsible for rotating secrets may not need access to retrieve every secret value in plain form, depending on how the system supports rotation workflows. Separating duties reduces the chance that one compromised identity can both retrieve secrets and alter secret controls. This is an example of limiting blast radius through deliberate permission boundaries. Logging is the part that turns secret storage from a black box into something you can trust operationally. If secrets are accessed and you cannot see who accessed them, when, and from where, you are operating blind. Safe secret storage should produce clear audit records that show retrieval events, changes to secrets, and permission modifications. These logs are critical for investigations, but they are also valuable for routine monitoring. If a secret is suddenly being retrieved far more often than normal, or from unusual contexts, that is a signal worth examining. Logging makes secrets access observable, and observability is a core security capability. Beginners sometimes assume that logging is only useful after a breach, but in mature environments, logging is part of prevention because it supports early detection. A compromised workload may begin retrieving secrets it never used before, or it may retrieve the same secret at a rate that suggests automation abuse. A compromised human account may attempt to list secrets or export them in bulk, which is behavior that stands out if you are watching for it. Logging also helps you validate that your access controls are working as intended, because you can see whether only the expected identities are retrieving specific secrets. When logs are reviewed and alerts are set for unusual patterns, secret storage becomes actively defended rather than passively protected. Visibility reduces dwell time for attackers. A subtle but important aspect of safe storage is ensuring that secrets are not exposed through accidental pathways, even if the primary storage is secure. For example, a secret may be retrieved securely but then printed into application logs, copied into error messages, or placed into crash dumps. Safe storage patterns therefore need to extend into safe handling patterns, where applications treat secrets as sensitive and avoid emitting them into outputs that are widely accessible. This is not about secrecy as a moral principle, but about reducing the number of places secrets can be discovered. Every additional copy is another opportunity for leakage. The more disciplined the handling, the fewer places defenders must search when something goes wrong. Encryption and access controls also need to be considered in the context of backups and snapshots, because secret systems are often backed up like any other critical service. If backups are not protected, an attacker might bypass vault controls by stealing backup data. Safe storage, therefore, includes ensuring backups are encrypted and that access to backup data is restricted and logged. It also means understanding retention policies, because a long-retained backup may preserve old secrets that should no longer be valid. If old secrets remain valid, backups become a time machine for attackers. This connects directly to credential lifetime reduction, because expired or rotated secrets reduce the value of old backup copies. Another common beginner misconception is thinking that storing secrets in environment variables is automatically safe because environment variables are not in source code. In practice, environment variables can still leak through process listings, debugging tools, logs, or accidental exposure in configuration management systems. They can be a temporary mechanism, but they are not a complete secrets management strategy, especially for long-lived production systems. A managed secret service provides stronger controls like access policies, audit logs, and centralized rotation support. It also reduces the need for humans to pass secret values around manually. Safe storage is about reducing human handling as much as possible, because manual handling increases accidental disclosure. Safe secret storage should also account for how different environments are separated, such as development, testing, and production. A major risk arises when the same secrets are reused across environments, because a compromise in a lower-risk environment can spill into production. Strong separation means each environment has its own secrets and its own access policies, and identities in development should not automatically retrieve production secrets. This separation keeps blast radius contained and aligns with the principle of least privilege. It also improves troubleshooting because secret usage becomes more predictable within each environment. Environment separation is not merely organizational, it is a security boundary. The concept of ownership is also critical in safe secret storage, because without clear ownership, secrets accumulate, become stale, and remain accessible longer than intended. Each secret should have an owner responsible for why it exists, who should access it, and how it should be rotated or retired. Ownership also supports incident response, because if a secret is suspected of exposure, you need someone who can act quickly and confidently. Without an owner, teams waste time figuring out who is allowed to rotate or disable a secret, and delay increases risk. Ownership turns secrets from anonymous artifacts into managed assets with lifecycle accountability. That lifecycle discipline is what prevents quiet sprawl. As you connect managed services, encryption, access controls, and logging, you begin to see safe secret storage as a system rather than a container. Managed services provide a standardized place to store and retrieve secrets, reducing ad hoc handling and hidden copies. Encryption protects confidentiality in storage and transit, while key management ensures that decryption is controlled rather than casual. Access controls enforce least privilege and separation of duties, preventing broad retrieval and limiting blast radius if an identity is compromised. Logging provides observability, supporting both detection and investigation, and it helps verify that the controls are actually working. Each element reinforces the others, creating defense in depth around one of the most sensitive resources in your cloud environment. By the end of this episode, the central takeaway is that secrets should be stored where they can be protected, governed, and observed, not where they are merely out of sight. Safe storage relies on managed systems designed for sensitive values, backed by encryption and strong key control. It relies on precise access policies that restrict retrieval to the exact identities that need it, with separation between reading and managing. It relies on detailed logging that makes secret access visible and actionable, so unusual behavior is detected quickly. When these practices are combined, secrets remain usable for legitimate systems, but far harder to steal and misuse. That is how you keep a cloud environment from being quietly unlocked by a single leaked key, and how you make secret handling a dependable part of your overall security posture.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.